Let's start the lecture, and we're going to have a new topic today. The topic is called Laplace transform. Okay. So far we covered how to solve first order, how to solve second order, right? But everything that we have been talking about is purely in this basically time domain. So whatever the original variable is, and we stay there, right? So we so in the time or in a function of x or function of anything. So we stick with that original variable. Okay. So now what we're having here is we're going to have a transform. Okay. So instead of let's say a time variables, and we're going to transform that into a different domain. Okay. So that kind of transform is called Laplace transform. Okay. So first of all, the definition. So given a causal function, so the difference is this is not called a system, this is causal function. A causal function means this function is 0 when t is less than 0. Okay. But when t is greater or equal to 0, there exists something there. Given the causal function f of t, then its Laplace transform. Okay, so we're going to denote this Laplace transform as capital F of s. Okay, or a different symbol, which is this. There's a curved L f of t. So this is basically an operator at here. Okay, this is basically like an operator and for a system. So what happens is, this is an operator, it takes the input f of t, okay? Then this L f of t is defined by this. Okay, so that's Laplace transform. So let's take a look at this simple integral right here. So L basically is an operator. Okay, it's functioning like a system. The input to the system is f of t here, and the output basically is going to give you a function capital F of s. So if you look at this integral here, what it does is it's integrating f of t multiplied by e to the power of negative st, and the dummy variable is t. Integrating from 0 to infinite. Okay, so apparently, if the dummy variable is t, then what's coming out of this one here? There's only one variable s left, right? So that's why you have a function of s at here, right? Yeah. So Laplace transform. Actually, this is called one-sided Laplace transform because it's a causal function, so there's only one side, 0 to infinite. In general, the definition doesn't restrict to causal. It can be extended to general function f of t. Then the definition at here, instead of 0, it'll be just negative infinite to positive infinite. Okay, so that'll be two-sided. So, but we're going to focus on this causal function. Okay, causal. The table I'll give it to you. There's a table of Laplace transform of the typical functions. They are basically all causal functions, but I'll talk about that later, right? Yeah. So, what's this s at here, right? This s at here. This s is a complex variable. Okay, it's complex variable. Sometimes we call that complex frequency variable. So if you want to bracket here, we can call this complex frequency variable. So s is complex, so we write s as s equal to sigma plus j omega. Okay. So sigma is the real part, and that omega is actually the frequency that we were talking about here. Okay. So we'll have a better understanding of this one. But for now, okay, this is just a purely mathematical definition of a Laplace transform. So now you see the wording transform, right? Why did it call transform? Because originally it's a function of t. After you apply this integral, and it give you a function of s, right? So basically, what we're hearing is what we're having here is the Laplace operator, okay? And you putting this f of t here. This is a t domain, okay? And it spits out f of s, which is the s domain now. So bear in mind that what happens to here, you're operating on the f of t here. So the Laplace transform actually retains all the characteristics of the f of t. Okay. So the purpose of this one here is transform. Basically, is you don't want to analyze the original signal in the t domain, and you probably wanted to analyze that in the s domain. Okay. So it's basically taking a look at the same thing from a different perspective. That's basically what happens here. It maybe helps, and maybe not, right? Yeah. But in this particular case, yeah, it actually helps in terms quite a bit of things, right? So one of the things is what we call is take a look at the frequency response of the system, right? So anyway, so first of all, basically understand that you're just taking a look at, okay, f of t, okay, from a different perspective, okay? So mathematically, there is in general, okay, so this is sort of additional here. You don't really have to write here. So in general, okay, there is so-called integral transform. There's so-called integral transform. The general format of integral transform is this: f of u equal, say, t naught, say t1 maybe, t1 to t2, k tu f of t dt. So there is this general integral transform formatted here. So if you look at this one here, so what does it mean is basically, here's your original function f of t, okay? Then you multiply by another function in here, and then integrate, okay, from t1 to t naught, and integrating by the t here, then you get a new function u here, right? So basically, this is a transform from the t to u, and this integral transform because the integral right here, right? So this key at here, we call that the kernel function. So if I relate this general one with the Laplace I was just giving you guys at here, so basically you look at this one here, this term in here is that k, well, in this here is not s, right? It's not u, but it's s at here, so this is kst at here, right? That's kst. If you look, compare this one with this one here, see that? Yeah, so that's basically, this is called integral transform. Laplace transform is integral transform. So then you can definitely say, oh, if I give this k of tu, if I give this function a different format, then I will have a different integral transform, right? Yeah, that's absolutely true actually. So after the Laplace transform, we'll have another one called the Fourier transform. So basically, it's a slightly different function, a kernel function in here. Okay? Yeah. As a matter of fact, if you recall that when we're learning impulse function, one of the property we learn is f of t multiplied by delta, let's say tau minus t, and then dt, right? Let's say integral from 0 to infinite, right? Remember this thing here? So, as a matter of fact, if you compare this with that one, this is a kind of a kernel function at here, right? Kind of kernel function. So what does this do? This one here, if you recall, this is delta function. Delta function is even, so this is t minus tau here, same as t minus tau. then f of t exists only at the t equal to tau. So overall, this is equal to f of what? Tau, right? Yeah. So this is a transform basically. Okay, and this is called identity transform. So anyhow, let's focus on this definition of Laplace that is here. Okay, Laplace. So let's see what good will that Laplace bring us here. Okay, but first of all, okay, what we're going to do is here's the definition. So we're going to look at the Laplace transform of typical functions. So typical function basically means unit step function, impulse function, sinusoidal function, exponential function, and what will be the corresponding Laplace transform, the one that I give it to you in the table here. Okay? Yeah. So, any questions? Okay? Yeah. I guess one thing I need to show first is here's the Laplace transform, then there is a corresponding one called inverse Laplace transform. Inverse Laplace transform. So inverse Laplace transform essentially is you give a function of s, okay, so basically give the transformed function, and then taking inverse, so L inverse here. Okay. And it'll give you back, supposed to give you back the time function f. Okay. The definition or the formula for the inverse Laplace is this: 1 over 2 pi j, okay, sigma minus j omega, sigma plus j omega, okay, f of s, est ds. Okay. So yeah, this is definitely a new thing that we have come across so far, right? Yeah, because previously every integral that you have done is in terms of real numbers, but this time this is an integral which involves complex numbers here. Okay, so there is a brand new, actually not really brand new, but there is a branch. It's called complex integral calculus. Okay, so in order to carry out this one here, you need to study this branch of calculus. Okay, yeah. So I was talking about the journey of a calculus. I guess it didn't really end there, but there's sort of a tension there, right? Yeah. So our focus is not on this one here. Okay. Yeah, we're not going to carry out this calculation here. So just in case you need to find out inverse Laplace transform, so what do? We're going to use the table, right? So the table, so basically saying, okay, I have a Laplace transform. So what is the corresponding f of t? So you don't use this formula here, you use the table. Okay. For example, if I have a function s1 over s plus 1, right? So you look at your table. I think you can find a formula like 1 over s plus a. Is that right? Does everybody have a table, the handout? Yeah? Okay. So that's on the second page. See, there's one at here. You see that? Right? So this is 1 over s plus a. The corresponding time function is e to the power negative at. I'll show you where this is from, okay? But how to use the table is, if you're giving e to the power negative at, then you should know that the corresponding Laplace transform is 1 over s plus a. Okay? If you're giving 1 over s plus a, then let's say, for example, 1 over s plus 1, then the corresponding time function is e to the power of a negative t. Okay, yeah. So this is actually an easy one. Many of this one here, I would recommend that you memorize them, not rely on the table. So we're going to use table. Okay, So now let's talk about a Laplace transform of typical functions. So basically, I'm going to show you some of these Laplace transforms shown in here, and how do they come, where they're from, okay? And by using the definition that at the beginning of the lecture. So first of all, let's take a look at the exponential function. Now remember, we're talking about these causal functions here, okay? So this is the way I write my causal function typically. Let's say this exponential one. So let's say a to the power of a negative. Let's use a at here. So since what did I use it in this here? A, right? Yeah. So let's use a at here. Okay. So let's say I have exponential function a multiplied by e to the power of negative at, and that's when t is greater and equal to 0. When t is less than 0, and it's 0. That's why it's causal, right? What's the other way of writing this causal function? Instead of writing it piecewise, exactly. Okay, yeah. Now in the table, I did not specifically say anything. Let's say, for example, I did not have a multiplied by u of t here. I don't have a multiplied by u of t here. But you should know that every one in here I'm referring to is a causal here, basically. Okay, so basically every function in here is like a multiplied by u of t. Is that clear? Okay? Yeah. So some weird symbols there, right? I think I mentioned the one part of here is all causal here, right? Yeah. Okay, so if I don't write it from now, if I don't write it multiplied by u of t here, you should know that I'm actually have a multiplied u of t is referring to a causal function. So let's say Laplace transform this guy. Okay, yeah. According to the definition, 0 to infinite, okay, and a, e, a, t. So technically, you should have this u of t at here. You should have u of t here. And but however, okay, because of u of t, you start integral from 0. But it doesn't matter even if I put a u of t here, because you started only exists the integral only exists from 0 to infinite. So this u of t here, actually you can get rid of them. Okay, get rid of it, because u of t is 1 when t is greater than 0, right? So this one here simply is just a 1. Is that clear? Yeah. So you don't really need this term in here. Okay. Okay. So this is the definition in here. There are two exponential ones, so let's combine these two together. So a, e, negative s plus a, t, dt. Okay. So we're integrating with respect to t. Okay, and so this s plus a term in here, you consider that as constant, right? Yeah. So this is basically exponential one here. Let's say I can take the a out of the integral. Okay. And if you can use substitution technique, but if I use my own technique, and what would that be again? So d negative s plus a t, right? But I have to divide it by s plus a negative at here in order to make it the same thing. Is that clear? Yeah. So there's this exponential one here. So the integral exponential is the same thing. So 1 over a over plus s plus a. Okay. And it's e to the power negative s plus a t, and t goes from 0 to infinite. Okay. Yeah. So that's the integral here. Any questions? Okay. Yeah. Yeah. Come again. this term, this term here, equal to negative s plus a dt. This term. So this negative bracket s plus a multiplied by that's going to be gone, right? So give me back this one here. So basically I'm trying to keep the same as the previous expression here. Is that okay? No? Yeah? Who's not okay with this? I guess most of you okay. Okay, good. So anyhow, so you don't have to do this, okay? If you're more comfortable with the substitution technique, just let u equal to what? U equal to this whole thing here, right? Then you do your own regular stuff, right? Yeah. Okay, so now I'm gonna plug in the t, okay, into this into exponential one here. But however, if you remember, the s, I said s is a complex number here. Okay, so let's put the s equal to sigma plus g omega here. Okay, so because I want to show you one thing, and once for all, just to show you this one here. Okay, so this is e to the power negative. So s plus a is the sigma plus g omega plus a. So I'm going to combine the sigma. A is a real number. Sigma is a real number. So I can combine this a and a sigma together. Okay, and that the t, okay, multiply this. Then minus this s is g omega, so that g omega t. Is that all right? Yeah. So take a second look at this one. Nothing really. Just plugging the s equal to sigma plus g omega into this expression, and then combine the real numbers together and single out this complex part. Okay. Okay. So if I plug in the sigma and infinite to the t at here, so what do I get? So I get e to the power negative sigma plus a infinite, right? And now this is e to the power of this minus that. So e to the power of a plus b equal to e to the power of a, e to the power of b, right? Okay. So this is basically e to the power of a negative j omega infinite. Okay. And minus, then you plug a t equal to 0 here. So when t is 0, plug it here, everything is 0. So e to the power of 0, which is 1. Okay, so that's what this one looks like. Okay, now focus on these two terms in here. Let's see what does that give us here. So first of all, this term, okay, e to the power of e to the power of negative j omega infinite. So what does e to the power of negative g omega infinite give us? Well, I guess if this is not infinite, let's say if this is some number here, let's say this is 2 or 3, then remember the formula, Euler's formula, right? So this one equal to cosine what? Negative j something here. No, j. Negative what? Omega that something plus j sine negative omega the something there. That's Euler's formula, right? Yeah. So really, this is infinite, but whatever you put it here, this is going to be cosine something plus j sine something, right? Yeah. But the magnitude, so this guy here, the magnitude of this one, it's not going to explode. It's actually going around what? Circle, right? Yeah. So this is basically this guy here. It's a bounded term. Okay, so this is not going to infinite. So what really gonna affect us is this term in here. See, right? So because this is real, right? This is real. For example, maybe this is negative 2 sigma. Maybe it's negative. Maybe it's positive 2 sigma. Who knows, right? So that really depends on what? Really depends on the value of sigma plus a. Okay, sigma plus a. So one thing for sure, if sigma plus A is greater than 0, then this term will go to 0. Right? If sigma plus A is greater than 0, this term will go to 0. Does that make sense? Right? So basically, if sigma plus A is greater than 0, then this term go to 0. Right? Okay. So this is basically a so-called region of convergence for this Laplace transform. So this guy here, sigma plus A greater than 0. So let me write it slightly different. I'm going to write the sigma as a real part of the S. Is that real part of the S, right? That's the real part of the S. Okay. So when the real part of the S plus A is greater than 0, or when it's greater than negative A, okay, then what we have here is this term go to 0. If this term go to 0, so what do we end up with for the Laplace transform? Basically, it's this guy multiplied by -1, right? So we end up with the Laplace transform f of s equal to 1, another 1a, a over s plus a. Okay, so this condition here is called region of convergence. Okay, so basically the Laplace transform, this term in here exists under this condition right here. Okay, yeah. So actually in that table, every result in the table has a region of convergence. But generally, as engineering application, we don't really care about this region of convergence. Okay, so we just make use the results. So we can just assume there is a region of convergence. Okay, and we're going to use the end results right here. So the step I'm showing here, I'm just trying to show is there's a region of convergence, but from now on, I'll just do the Laplace transform and without mentioning this region of convergence. Is that okay? Yeah. So now, if you look at this Laplace transform here, if A is 1, right? If A is 1, you get what you have in the table. Okay, so second one here. Let's take a look at unit step function. So Laplace of a unit step function. So in the table, you can see that Laplace unit step function is supposed to give you 1 over s, right? 1 over s. So let's see if that's the case here. Okay, so according to the definition, it's a 0 to infinite u of t e to the power negative st dt. Now because u of t here is 1, so this guy, right, is gone. Okay, so this is just basically an integral of exponential function. You consider s as a constant, right? So that gives you this -1 over s, okay, e to the power of negative st 0 to infinite. Right, 0 to infinite. Again, you can change the s into sigma plus j omega, okay, and there is this region of convergence. Okay, so you end up with just basically 1 over s. Okay, in this case, the region of convergence, okay, is the real part of s has to be greater than 0. Okay. Okay, so that's how you get this u of t here. So I'm not going to show you everything, okay, but essentially every results in the table, okay, can be derived by apply this definition of Laplace transform. Yeah. Yeah, Dustin. Well, basically, how do I get this guy here? Under what? Under this condition, right? That's basically region convergence. If I don't have this condition here, that term exploded. That makes sense, right? If this real part of s or if sigma plus a is less than 0, for example, if sigma plus a is less than 0, what happens to this term? It's not converging, right? It's diverging, basically. So you won't have this result here. So that's why I call it region of convergence here. And this is the results of Laplace transform. So we don't really care about the divergent part. There's nothing there. Okay, there's no results giving us. However, we discard this concept region convergence. We only focus on the end results of this Laplace transform, which is the table of the results I give it to you guys. Okay, so that's the logic here. Okay, yeah. Okay, so similarly, you can also get if this is f of t equal to t square, not t square, t ut. So when you have a t multiplied by u of t, and you'll have this corresponding Laplace transform by applying the formula, which is 1 over s squared. Okay, 1 over s squared. Okay. So take a look at many of these typical results. I did give you a proof in the lecture notes here. Okay. So feel free to go over the lecture notes and try some of this proof by yourself. It's an exercise of integral, right? But I do want to show you one of the proof at this one here. Basically, it's a sinusoidal one. Okay. So let's say I have a sine omega t at here. What is the corresponding Laplace transform? This is very important, a very important function. Okay. The reason is basically I'll show you is the reason we learn Laplace. One way is to analyze system. The other way is actually we're going to use the Laplace transform to solve second-order differential equation, right? Yeah. So before we take a look at the Laplace transform, this one here, let's if you recall that, okay, if you recall that when we have e to the power j omega t, according to Euler's formula, this is cosine omega t plus j sine omega t, right? Yeah. So then, if I take Laplace transform of this guy here, Laplace transform of e to the power j omega t, so what will be the corresponding Laplace transform? Well, what do we have? What have we derived? We derived the Laplace transform e to the power of negative at, right? So let me write it down here. So Laplace transform e to the power negative at is 1 over s plus a. If I change this slightly here, if I change this to positive a, if I change the positive a here, so what will be the result here? Minus, right? It's minus. Okay. So now if I compare the two results here, so basically this a is which term? J omega, right? J omega. So then the Laplace of e to the power j omega is 1 over s. What is it? According to results here is minus j omega. Okay? Yeah. So this is 1 over s minus j omega. And if I wanted to use this division of the complex number, so basically s minus j omega s plus j omega, so multiply its conjugates. Right, so that's how I simplify it. Then the bottom here becomes s squared plus omega squared. At top is s plus j omega. Okay, yeah. And that equal to s over s squared plus omega plus j omega over s squared plus omega. Is that clear? Right, that's basically a simple complex number operation, right? So multiply by the conjugate. So what is the e to the power j omega again? It's this guy here. Right, it's this guy. So if I plug this one into this bracket, okay, so then I'm going to rewrite it here again. So this is Laplace cosine omega t plus j sine omega t, right? Okay. So later you will see there is a property here. Basically, Laplace operator L is a linear operator. Okay, linear operator. Why is it linear operator? Because actually we actually did a lot of practice. Because you look at the definition here, what's here? Laplace basically is an integral, right? And integral is a linear operator. So Laplace operator is a linear operator. So when it's a linear operator, you have this so-called superposition property. Okay. So all of this constant here, you can take them out. So basically, this is equal to L cosine omega t plus J L sine omega t. Okay. So you consider the G as a constant essentially. Okay. This is Laplace of E, which is this. The result of the Laplace of e to the power g omega is this. So now let's compare this one with this one here. So you see the similarity? There's a j multiplied this, there's a j multiplied this, and there is this s this here. So which means what? This Laplace of cosine omega t is this. Laplace of sine omega t is this guy here. That makes sense, right? Yeah. So which means Laplace of sine omega t, okay, is omega over s squared plus omega squared. Okay, that's it. Yeah. Laplace cosine omega t is s over s squared plus omega squared. So this is where they're from. Okay, this is where they're from. Okay, so this is number 4, right? Yeah. Any questions? Yeah. You mean here? No. See, this G corresponding to this G here. Yeah. Yeah. So in Laplace transform, okay, one thing, you shouldn't have any G there. Okay, even S is complex. Okay, so everything should be a function of S basically. Okay, it should end up with a function of S. Now there is a property of this one here, basically e to the power negative at multiplied by f of t. So sometimes we have a exponential function multiplied by f of t. Remember when we're solving second order differential equation. Now when the input is e to the power of negative, let's say input is an exponential function multiplied by sinusoidal, right? So what do? You go to the table, you find a lucky guess from the table. Okay, yeah. So this is basically that type of input at here. Okay. So for this kind of here, there is a property of this one here. This is going to be equal to capital F of s plus a. Okay, and this f of s equal to the Laplace f of t. So in the lecture notes, I showed you the proof of this one here. Okay, so there is this property of this. So when you multiply f of t with the exponential function negative at at here, the corresponding Laplace transform is f of s plus a. So what happens at here is when you multiply this one here, you don't really have to calculate this one here. What happens is just what? You're just shifting this one to the left by how much? A, right? That's what happens at here. So for example, if I have this EAT cosine omega t, so what is the Laplace transform this guy here? According to the property. Yeah. This s will change to s plus a. That's right. Okay. So this will be s plus a at there. See, this is the Laplace cosine omega t, right? So change the s plus a. Okay, yeah. The omega, you don't change. So you can see that similar results in the table there. Okay. Yeah. So some of the exercise, the homework that is basically trying to make use of properties. I'll give you a few more properties, okay, to do this Laplace transform. Okay, so one more here, impulse function, delta t. Okay, so this one, you need to memorize this one here. Okay. So for delta t, so what we do is, let's start not delta t, let's start with the t minus a. Let's start with the delta t minus a. Suppose a is greater than 0, okay? Then Laplace of this delta t minus a, okay, according to the definition, 0 to infinite delta t minus a e power negative st dt. Right. Definition. So from the definition, now we're going to apply the properties of the delta function. What are the properties of the delta function? Basically, if you look at this one here, this is a function of t here, right? This is a t, and which exists only at a t equal to a. So then we're going to replace this t with a. So then you can take that part out of the integral. Okay. Yeah. And this integral here, the delta t minus a, and this in 0 to infinite a greater than 0. So basically this guy is what? 1, right? Yeah. So that's the Laplace transform delta of t minus a. But what we want is delta t. So then what do? We set a equal to 0. So then we end up with, so a equal to 0, 1. Right? 1. So that's the Laplace transform of delta t. Now, it's called 1, right? But actually, because we're talking about causal function, this is actually what? U of t, exactly. Okay, this is basically a unit step function. Okay, yeah. Is that clear? Okay, good. So those are typical Laplace transform typical functions. Okay, there are some properties I think you need to know. Okay, those particularly couple of properties, very important property in terms of solving second order differential equation. Right? One of the property actually I showed you here. This is one of the property here. Okay, this is one of the properties. So maybe I'll just write it down again. Actually, the first one is the linearity. Okay, linearity. So linearity basically is the superposition rule. C1 f of t plus C2 g of t equal to C1L f of t plus C2L g of t. So this is basically a superposition. Okay. And the other one here is that the property, this property L e to the power of negative e to the power of at, okay, f of t, which equal to capital F of s plus a, right? And always remember, it's when we have a capital F there, that's the Laplace transform of f of t. So this is another property. This property has a name called frequency shift or S shift. Okay, that's the second property. Okay, so sometimes you can use this one here to get what you want. The third is the time shift. Time shift. So the time shift is like this. So Laplace, okay, of a shifted function. Okay, shifted function. Right? So this is basically, originally it's f of t ut. So f of t multiplied by u of t give you a causal function, right? Give you a causal function. So then we're going to shift this whole thing to the left, to the right, by amount of a. And what will be the corresponding Laplace transform, right? Okay. So for this particular case, what you're going to have here is e to the power of a negative as capital F of s. So capital F of s, the Laplace transform of f of t here. Right? So that's another time shifting. I have the proof in the lecture notes, and so take a look at that if you want. Okay. Yeah. So just bear with me. I'll write down one more property, or even two, just in case. Okay, this is actually the most important property that you'll use a lot. Okay, so this is called time differentiation. So many of the property here, because of time constraint, I won't be able to show you the proof. So I would encourage you to go over the proof in the lecture notes. So time differentiate of this one, basically, what's the Laplace transform of the derivative, okay, of this function? Okay. So what's the Laplace transform of the derivative function? So same idea. So what you do is you plug in into this definition. So this is the definition here. Okay, the definition. So very simply, you can take a look at this one. If I plug in this one here, this dt got cancelled, right? So you end up with 0, infinite, est df of t here, like this. So then next thing what you do is, what comes into mind? Integral by parts, right? So this is basically you're going to do the integral by parts here. So, but I'm not going to do it again. So then in the end, what you're going to end up with is this: s capital F of s minus f of 0. Okay, f of 0. So the derivative, Laplace derivative of function f of t, give you s capital F of s minus f of 0. So this f of s is the Laplace transform of f of t. F of 0 is the initial condition, right? So that's basically the derivative first order. Similarly, you can get a derivative second order. It'll be s squared, okay, capital F of s, minus s f of 0 minus f prime of 0. Okay. So this should be on the first page of this table there. Now these two, okay, are very important properties. You're going to make use of them a lot. Okay. Yeah. Any questions? Okay. So we're going to take a look at the applications in the next lecture. Hey, how are you?
Do you have any more of the table?
Oh, yeah. Do I? Is there any leftovers? The table? Is there? No. Interesting. Okay, but I'll upload to the